let's begin with transverse. So this is an example of a transverse wave and what it looks like. You have to remember that the motion of the medium in a transverse wave moves perpendicular to the direction of the wave travels. So if you look right here, notice the wave is moving up and then moving down. So the medium is perpendicular to the direction of the wave. Here's the wave moving this way. Perpendicular, remember, perpendicular, 90 degrees too. The wave travels along the medium but only moves up and down. These waves can only move through solids. That might be something you want to know. Only move through solids. So when we're looking at transverse waves, this would be example. We're going to actually diagram this so you guys have an idea of what we're talking about. So the highest point above the equilibrium, first of all, this line right here, that's when the object's at rest. Otherwise known as equilibrium. So that's when it's not moving. If you're moving a pendulum back and forth, that's when it's at rest before you ever start to move it, okay? So this doesn't mean up and down necessarily. It means opposite directions. So on our transverse wave, that is at rest. The highest point above the equilibrium, or the highest point above when it's at rest, is going to be a crest. So this is a crest. Which obviously then the lowest point is going to be a trough. So we have a crest, we have a trough. The crest is the highest point, the trough is the lowest point. So then we have amplitude. Now the amplitude is the distance from the rest position to a crest or to a trough. So basically this or this can both be amplitude. So the distance between the rest position to a crest or to a trough is the amplitude. And then next we actually have the wavelengths. So wavelength is the distance between two adjacent similar points. So on a wavelength, you can go trough to trough. This would be one wavelength. Or you can go from crest to crest. So this would be one wavelength. Just a little note, we're going to get into more of this when we start calculating things, but the symbol for wavelength
First off, wavelength. Lambda. A wavelength is the length of a full cycle of a wave, from one point to the next same point. It's easiest to think of as the distance from crest to crest or from trough to trough. And we measure it in meters, and it's given the symbol lambda, a nice Greek symbol. The amplitude is like the size of a wave, but we need to remember that it's measured from the equilibrium position, or the central line, to the crest, not from the crest to the trough. Finally, frequency, which is the number of complete waves to pass a point every second, and it's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave using the equation speed equals frequency times wavelength, or to give it in symbol form, V equals F lambda. So there's a lot to learn here, but once you've learned these core concepts, it will give you much more confidence.
So a longitudinal wave, the motion of the medium is parallel to the direction of the wave travels. So if your wave is traveling this way, notice the medium is traveling this way as well. So it's parallel. They're going the same direction as. These types of waves, these longitudinal waves, they only apply to spring and coil compression. Like think of slinkies. So these are also called compression waves. These are also called compressional waves. And when this happens, you got to realize that only one spring or coil actually compresses at a time. Okay? So let's label our different parts of a longitudinal wave. To begin with, we have the actual compressions. That's where things are close together. So this would be a compression. The opposite then of the compression is when we have everything all spread out, right? This is called a rarefaction. 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 So when things are squished together, it's a compression. That should make sense. And when things are spread apart, that is the rarefaction. When you have a wavelength, that's going to be your distance between two similar points, just like in the transverse wave. So whether you're measuring from rarefaction to rarefaction, or you're measuring from compression to compression, these are all your wavelengths. And remember, this is a symbol for wavelength.